Hello everyone and welcome back to this next lecture. So in the previous lecture, this is where we had left off. We were looking at these two links, or rather these two online resources. This is on the Numpy FFT module. So there were two methods I was saying are interesting. So the first method is the FFT method itself. This is the method that will actually perform discrete Fourier transform using the FFT algorithm, which is the fast Fourier transform algorithm. We will also use the FFT freak method within also the FFT module, but this is more for generating the frequency range, which we will see very soon why we need it. Right? So I hope you have read these two online resources. If not, please pause the video once and go and have a look for yourself. The reason is it'll be good if you use, or rather read it once on your own and try to see whether you can understand it. If not, go back and watch my previous video and then come back here again. We will gradually build on this, so take your time, read, stop, watch again these videos if you need. This is slightly complicated. As I said, the examples are not very clear, so we're going to have to slightly, it almost will seem like we are groping in the dark at times. Alright, so let me go over to my code. So this is where we had left off. We had generated the modulating signal, we had generated the carrier signal, we had defined this output signal. Let me go back to the original definition. Let me just delete this one and let's go back. We can always revert if we need. And we were plotting this, right? So let us continue plotting, that's not a problem. But now we are going to introduce our FFT methods. So if we need, go back always. You can always have this for quick reference. We must import these two modules. We have already imported Numpy. We need to import the FFT module and we need to import this FFT freak module. So you can import the entire FFT module, but as I said, I would rather import exactly what I need rather than going about importing everything. Right? So let me come over here and say from numpy.fft, because remember there is the FFT module within Numpy, import FFT, and there is the FFT method. So there is the Numpy module, within the Numpy module there is FFT, and within FFT there is the FFT method, and there is the FFT freak method, right? So these two methods I am importing. Now let's come down here, and first thing I'm going to do is let me just comment this, because I would rather start with actually exploring this FFT method. So let's not generate any plots. Okay, I'm going to delete all of these, or rather comment all of these. So let's go back here and see what we're doing. As I said, in our case, we do not need to specify these other arguments. We have an array on which we are trying to do frequency analysis. This array, in our case, is the output modulated signal. Though it can be anything. We can also do frequency analysis on the modulation signal or the carrier signal, right? We can do frequency analysis on any signal. But right now our interest is in performing frequency analysis on the output modulated signal to figure out which frequencies are present in that signal, right? So as I said, we do not need to specify the others. This one array contains all the information we need, because by definition, if we have a window of n samples, if we take a function, we have n samples of that function, then in that case performing FFT will produce a window with n samples of frequency. Alright, stop for a minute and think about this. If you need, go back and read this thing and you will see that we have a finite window of n samples of our function. This function is the output modulated function. We are performing DFT on each and every sample on this function, or rather in this window, and this summation will be performed for each and every sample, and this will result in another window of the same number of samples of frequencies. Okay, sometimes a little confusing, but doesn't matter, we'll continue with it. So, okay, I think we need to come back here. So all we need to do is call FFT of this output modulated signal. So let me come down here and let me start with that. So I'm going to come here and write some equations, or rather comments. So I'm going to say DFT on the output modulated, let me call this signal. So let me now use, I'm going to call this DFT output. This DFT output is going to be FFT into whatever signal we want to choose, right? You see, it's giving a help. It is saying you can choose any signal. This can be any, it can be any array, it can be a Numpy array, it can be a multidimensional array, it can be anything. We are not going to use the others, right? We are going to have only one array, and I'm going to choose this to be the out signal. All right, so let me write here, performing DFT using FFT on Y of t. All right, this is what we want to do because we want to perform frequency analysis on this. Now, before we actually start plotting anything, let's go try to find out what this is. And let me go over to my command line. And as always, I will start with activating my SP environment. Make sure that SP appears in parentheses so that I know the environment is active. Then I will go over to my folder which I have created for this course. Within that, I'll go to the folder for this particular chapter, and I'll make sure that the file is there in this particular working directory. If I try to run the file directly without going into the correct folder, it will give me an error saying the file is not found. So now I can run the same file. Alright. Alright, so this is our output. Take a look at what's happening. These are, as you can see very clearly, complex numbers. Right? This is the scientific notation. It is 1 e raised to minus 10 plus 0, 1 point something e raised to minus 10 plus 2 point something e raised to minus 11 g. Right? This is a complex number. This is the real part. This is the imaginary part. And in this manner, there are lots and lots of these. So what is going on? Let's go back here and read the documentation. What does it provide? The output is a complex Numpy array. Alright, why is it complex? Come back here. You'll see we are multiplying the function, each and every sample of the function, which is a real number, with a complex exponential. This complex exponential. So we are multiplying numbers, real numbers, with complex numbers, and therefore the summation will also be a complex number. Right? So the Fourier, the frequency samples that we are getting are actually complex numbers. Right? So therefore, the first thing we need to do is we need to figure out how we can convert them into real numbers. As already stated, and this is something which I've talked about in the lecture. Say for example, if you come over here, I have said that this frequency, the value of the function at a particular frequency, is a complex number. This has a magnitude and it has a phase angle. The phase angle of this frequency component, when combined with this complex exponential, will give you the actual sinusoid with the phase angle, actual lag or lead. But what we are interested in is the magnitude of this frequency component, the magnitude of the value of the function. That is all we are interested in. So which means we can't directly, there's no point in directly using this particular DFT output. Let us now include another line here and say DFT output magnitude. Let's call it mag. And here I'm going to use the NP ABS method. The ABS method is calculates the absolute value. So for example, if you come and have a look at this, this is the help, is a shorthand for this function. It takes any array and it calculates the magnitude. You can read this if you want. I'll just tell you quickly. It will calculate for a complex input. It will calculate the absolute value. So if there is a complex input, a plus jb or a plus ib, however, a and j and I are the same, then the absolute value is the square root of a squared plus b squared. This is the magnitude or absolute value of any complex number. So this is what we're going to do. So if we apply this function on a numpy array, it is going to return another array with the magnitudes, which is what we want. So let's do that. And here I'm going to now print out magnitudes. Right? I'm going to print out this array here which we've calculated. Let's see at least if it is a number. At least we want a numpy array of numbers. So let me go and run the program again. And you can see it is now returning real numbers, right? They seem strange, right? They do seem strange, and we'll talk about that very soon. But you see it is at least returning real numbers. Okay, so let's come back here. So the first thing we need to do now is we need to see how to make sense out of this. So if we take a look at this, let's now try to plot it out, because now that we've printed it out, there's no point, because this print doesn't show everything, right? Because you see there's dot dot dot. Dot 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 just means that we have a lot of numbers and it just is not wanting to show each and everything. But we do not know actual values, because remember, not all of them will be e raised to minus 10. There will be some which are significant. So let's try to figure out what's going on. So I'm going to delete this print. We don't need that anymore. And let's start plotting waveforms again. So I'm going to plot now this FFT output. So I'm going to just write here plot frequency response. So I'm going to create a new figure and I'm going to say plot plt dot plot. Now what are we going to do? Here is the major question, right? Now so far we are not yet using this FFT freq method, and I want to slowly build up to that. First, let us figure out what is this FFT producing. Now you can plot any array just as it is. In that case, it will plot the array with respect to the index numbers. So that may not make much sense, but let's just do that anyway. So I'm going to say DFT and output mag. So we need to come down here and we need to uncomment this plt.show so that we can still see the plot. And I'll come back here, clear the screen and run the command again. Alright, so it's a fairly interesting result. Take a look at what's going on. Most of the screen is blank. Alright, I hope you've reached this stage. If not, post in the Q&A forum and I'll help you out. But I hope you're coding along with me and I hope you got this. Most of the screen is empty. Remember, we are plotting simply the magnitude with respect to the index numbers of the array. See, these are all the index numbers. E raised to minus, see, this is not 0 actually. It is 0 multiplied by 1 into e raised to 6. So this means 0.2 into e raised to 6. What that means is 200,000. So this is 0, this is 200,000, 400,000, 600,000, 800,000, 1 million. The reason we have 1 million data points. Alright, if you don't know how that is, come back here and check for yourself. We have a duration of 1 second. We have a time step of 1 microsecond. And that means we have 1 million data points. So therefore our arrays are 1 million in length. And that's what it's trying to do. Now let's try to zoom in and see what is happening here. So we seem to have some interesting results. Something is happening, right? Something is happening. Now, see what's happening here. It says 5,000, and at 5,000 we seem to have some non-zero values, but these non-zero values are huge. What's going on? Look at this. It is 250,000 at 4950, right? Now here your brain should be ticking. There is some frequency component at 4950, and there is another frequency component at 5050, right? Look at this, 4950, 5050, right? So we seem to have caught hold of something. Something is happening here. But the question is, what is this value? It makes no sense at all. We can't have a frequency component of 250,000 when we are generating a waveform just of one magnitude, right? Go back and have a look at the amplitude waveform, or rather the amplitude modulated output waveform. It is simply a waveform with a maximum magnitude of 1. So this simply is rubbish. So the first thing we need to do is, let's try to figure out what's going on here. And here, unfortunately, the method or the command doesn't tell you what's happening. This is something you have to actually use some intuitive thinking here. Let's come over here and have a look. By definition, the Fourier transform, this Fourier transform, let's go back here, sorry. The continuous time Fourier transform is an integral. We are integrating this function over all time. We are multiplying the function with the complex exponential, and we are integrating it over all time. But there is a difference between integration and summation, right? This is the continuous time Fourier transform. In the discrete time Fourier transform, we are taking a summation. We are taking a summation of this product. Now, there is one huge difference between continuous time integration and discrete time summation. In continuous time differentiation, or rather integration, we are multiplying this product with the time step. So really speaking, this integral happens over infinitesimally small time steps of the function, right? This function, we will plot this product. See the product now, we have the function, we have the complex exponential, we are taking the product, we get another function. We are taking this function and we are taking the area under this function. And the way we do it is we take infinitesimal small strips and we are adding those strips. But this process of taking these infinitesimally small strips is that this function is automatically normalized. The integral is automatically normalized, right? Now think of it this way. If we were doing a numerical integration, right, a numerical integration, we would take a time step. Like for example, we would take 1 microsecond. We would take the value of the function, the value of the exponential, and multiply it by our time step, and then we would sum it up. But if you come over here and have a look, there is no such time step. There is no time step. So we are actually multiplying the value of the function with the exponential. We are summing it up, but it is at a totally different scale, right? Now here, please pause the video, go back and have a look. This is not a very easy concept, and therefore you really need to know. This is an implementation method. If you have done any numerical integration, you will know what I'm talking about. If we were to implement this integral in a computer, right? If let's say we wanted to do this in a computer, we would have to take samples of the function, we would have to take samples of the exponential, multiply this product, and we would have to multiply this product with the time step. If we have a time step of 1 microsecond, we'll be multiplying it by 1 microsecond. Then each and every element we'll be adding it over completely. This is what we would do. But in this summation, there is no time step. And that is precisely the reason why we are getting this huge number, because it is not scaled. We have to scale it. So I'm going to close this screen, come over here. How do we scale it? We need to scale it by saying we can't interfere with this method. There is nothing we can do. So what that means is we need to scale it additionally, that we need to scale it externally. The way we scale it is we have to bring in a factor equivalent to the time step. There are two methods. We can either multiply by t step, or we can divide it by the number of data. They are both the same. If we multiply it by t step, we are multiplying by 1 microsecond. If we are divided by the number of data, we are dividing by 1 million, which again comes to 1 microsecond. So I will just multiply this by t step. Alright, let's go. Let me see, did I save the file? Yes, I did. Okay, let me go back to my command line. I'm going to clear the screen and I'm going to run the command again. Fantastic. Now we have a much better result, right? We have a much better result. Only thing is we still are having a little bit of a tough time figuring out what is going on, right? Now here, this shows that there are two components, one at 4950, one at 5050, and they are both 0.25. This is very close. Alright, very close. Now if we come back to our amplitude modulation, actually I don't have the slide, but go back to that slide of amplitude modulation and you will see that we have 0.5 for each frequency component. So we seem to be lost a little somewhere, but there's nothing wrong. This is merely a problem with interpreting the results. The reason is because now we have, actually let me just zoom out. The problem is with this frequency. We are not taking into account this frequency, and let me just zoom in and show you why. You will find that there is a similar case here as well. Right? There is exactly the similar case. And this is close to 995,000. Almost close to the end of the spectrum. Now you might ask, what is going on? Right? It makes no sense at all. The first one made some sense. Right? This one makes some sense because this is the frequency we were expecting, at least mathematically. But what is this frequency here? It makes no sense at all. But in reality, this is just how the Numpy function works, and this is why we need this FFT frequency method. Right? Now, I hope you have gotten this far. If anything is not clear, please do let me know in the Q&A forum and I'll be happy to help you out. Remember, it's quite simple. The first thing is we have to take the FFT of our output signal, or whichever signal we want to perform a frequency analysis on. Alright, we can even perform a frequency analysis on the carrier signal or on the modulation signal. Right? Only other thing we need to take into account is that because this FFT method is a brute force summation, the results are at a totally different scale. We need to scale them down. Alright, we need to scale them down. We need to scale the results down, and for that we need to multiply this entire result, or rather every element of this array, by t step. And of course, we are only interested in the absolute value or the magnitude of these frequency components. We don't care about the phase angle because these are complex numbers. So we are doing an np.absolute on the DFT output. So if you still have any doubts, if something is not working, please do post in the Q&A forum and I'll be happy to help you out. Otherwise, in the next lecture, I'm going to talk about how we are going to use this FFT freak method, or frequency, however you want to call it, FFT freak method, to be able to scale our frequencies such that we can actually get a sensible output which we can interpret. So thank you so much for listening, and goodbye for now.